We're going to discuss diode AC circuits, particularly rectifiers. Okay, so what is the difference when we say AC circuits? So for AC circuits, we will be applying an AC signal to your to your diode circuits. Okay, from our previous video, we just applied a DC source. So with a DC source, it will just be for us to determine whether your circuit is in forward bias or reverse bias mode. So we're just going to analyze once, because when we apply a DC source to your diode circuit, it will not be changing or it will not be varying, unlike an AC source, because an AC source, sometimes your diodes will be forward biased, and other times your diode will be reverse biased. So we really need to analyze your circuit more carefully when applying an AC source. Okay, so the first diode application with AC source is what we call rectifiers. Okay, so what are rectifiers? A rectifier circuit converts an AC voltage into a DC voltage. Okay, so our input will be initially an AC source, an AC signal in a form of a sinusoidal waveform, and then upon application or upon passing through a rectifier diode circuit, we can measure a DC voltage on it. So using a DC voltmeter, we can somehow measure a DC voltage across our output or our load. There are two types of half-wave rectifier circuits. No, we have the half-wave and we have the full wave. So we're going to discuss each one by one. Um, Usually, we can find the practical application for a rectifier circuit in a DC power supply. Okay, so a DC power supply operates from an AC voltage source and will give us a DC output that we will be needing in our circuits, for example, in the laboratory. Okay, so this is an essential part of each electronic system, from the simplest to the most complex. So we have what we call a simple DC power supply, and then later on we have what we call a regulated power supply. So if we're going to look at the block diagram of a power supply, we have an AC source. Okay, so this is coming from an AC source. So we have here 110 volts AC with a 60 hertz frequency. In the Philippines, we are using 220 volts. Okay, so this 110 volts here, or the 220 volts here, are the what we call the RMS value. So unless otherwise specified, we are using the RMS value. So in AC source and AC signal, we have different terms that we can use. So we have the RMS voltage, we have the peak voltage, we have the peak to peak voltage. So unless otherwise specified, it is the RMS value. So the value that we are usually given. Okay, but later on, we're going to find out that there is a relationship between the RMS value and the peak value, and then later on, peak to peak value. But if we're going to make use of an oscilloscope, so in your laboratory, you will be using an oscilloscope. Usually, what we see there is a peak voltage or a peak-to-peak value. Although there are some oscilloscopes that are capable of giving us the RMS value also. Okay, so our DC power supply is divided into three blocks. Okay, so from the source, which is an AC source, we will be passing through a rectifier circuit. So a rectifier circuit will convert your AC voltage into a DC voltage. So this is an important or an integral part of your DC power supply. And then later on, you're going to pass through a filter. So sometimes this is just a normal RC filter or just a capacitor filter. And then later on, we will be passing through a regulator circuit. So we will be discussing the regulator circuit, the simple type of regulator circuit, which is made up of Zener diode on our next video. Okay, so by looking at this diagram here, this block diagram here from an AC source, from a sinusoidal waveform, we have an output which is regulated at DC. So this is our representation for AC, which is a sinusoidal waveform, and this is our representation for DC, which is a straight line, which means this is not changing. With respect to time, its value is constant. Unlike our sine wave here or our AC signal, as time progresses, the value changes continuously. Okay? So, and then what will appear at the load is your regulated voltage. So we will be starting with the half-wave rectifier. Okay, so the process being performed by a half-wave rectifier circuit is what we call half-wave rectification. So what happens when we have a half-wave rectifier? So we have here, for example, an input of 110 volts 60 hertz. Upon passing through a rectifier circuit, our waveform is like this. So what did you notice? It's like the half, okay, the negative half cycle was removed. Okay, so the only thing that we have there are the positive half cycles. So what happened? So partly, your circuit is no longer a sinusoidal waveform because the half wave was removed. So partly, we have already converted some AC signals into a DC signal. Okay, so this is a simple half-wave rectifier circuit. So as you can see, this is just like a series parallel configuration. Okay, wherein your diode here is connected to your source. However, our source symbol here is already in the form of an AC signal. So that means we have two half cycles here. So we have the positive half cycle wherein we have your plus and minus here, and then we have the negative half cycle later. So during the positive half cycle, what happens? So we have here your positive, which is connected to your anode. Okay, so once it is connected, so we can see that this diode here is in the forward bias mode. So when the diode is in the forward bias mode, what happens? This serves as a short circuit or a closed circuit. So therefore, your current can pass through your diode. And then when current pass through your resistance here, we have a voltage drop across this resistor. So the voltage drop here is equivalent to the current which will flow here and to be multiplied by the resistance here. Okay, so what is the output? Considering this as an ideal diode, we have here that your output is totally equivalent to your input signal here. However, your signal here is changing. So let us say when your input is 0, your output is also equal to 0. So when your input is increased, your output is also increased. When your input reach the peak value, so this is our peak value, your output also reach the peak value. So whatever your input looks like, your output will also look like as your input here. So that is during the positive half cycle. Okay, so the difference is that since this is the load, so this is where we're going to get your output. So the difference in the DC source is that when we apply a DC source here, it is just like this one. Okay, so it is not changing. There is no positive half, and then there is no negative half because your source here is because your source there is said to be constant. Okay, so the difference when you have an AC source is your source here is changing. So sometimes it is plus and minus during positive half, and other times it is minus plus. And also, when we place a DC source which is equivalent to 5 volts, all throughout, the voltage is 5 volts. But when we apply an AC source, sometimes it is 0, sometimes it is 5, sometimes it is 10, sometimes it is 9, and so on. So it is changing. It has point 0.1, point 0, and so on. So it changes continuously with respect to time. So that is the main difference of having a DC source and an AC source. Okay, so going back here, what happens during the negative half cycle? So during the negative half cycle, we have here the minus and plus. So we have here minus and plus. So the negative is connected to your anode while the positive is grounded. So what happens? Negative to anode, this is a reverse bias condition to your diode. And at reverse bias condition, your current is equal to zero because your diode here is operating as an open circuit. So therefore, when your current is equal to zero, no current flows across your RL. This is technically an open circuit. So therefore, when no current flows across your RL, you don't have any output. So during the negative half cycle, our output is equal to zero. And then, it will be going again to the positive half. So positive half, your diode again becomes forward bias, and we have another output. And then negative half again, it will become reverse bias. So we don't have again another output. So if we're going to combine this now, this is our output waveform. So our output waveform is equivalent to this one when we are forward biased, this one when we are reverse biased. So this one during positive half cycle, this one during negative half cycle, and the cycle continues. Okay, so that is why that is your rectifier circuit. It is just like a simple series circuit, but we place an AC source instead of DC. So you're going to analyze it two ways. One during the positive half, which will forward bias your diode, and the other one during the negative half, which will reverse bias your diode. Okay? Okay, so what is important in rectifier circuit is knowing how much DC source was converted out of your AC source. Okay, so that DC source that was converted from your sinusoidal waveform or from your AC source is what we call your average value. Okay? So the average value or the DC value. So V average or DC average. So for example, we have a load resistor here, and you have a DC voltmeter. Okay? So you have a DC voltmeter. When you check for the output voltage here, you can read a DC voltage. So that DC voltage is what we call the average value of the half-wave output voltage. Okay, so this is the value that you would measure on a DC voltmeter. So this is determined by finding the area under the curve over a full cycle and then dividing by 2 pi the number of regions in full cycle. Okay, so if we're going to look at the value for that, that is equivalent class to our V average or our VDC is equivalent to VP or the peak value. Okay, so we are now specifying the peak value. So if the given value is the RMS value, we have to convert it first into peak value. So later I will be giving you the relationship between the peak voltage and the RMS voltage. Okay, so the V average or your VDC is equal to the peak value divided by pi. So if you're going to press that in your calculator, that will give you 0.318 multiplied by your VP. So the converted DC or the average value is equivalent to 0.318 or 31.8% of your peak voltage. Okay, so how did we get this? So this is finding the area. Okay, so this is the area under the curve for a full cycle and then dividing it by 2 pi. So what type of waveform do we have? We have a sinusoidal waveform. So if we get a strip here and then we get the area, so that is 1 all over T or 1 over period in getting our V average. So that is from 0 to time of our value or of our input voltage. Our input voltage happens to be an AC source. So an AC is represented by an amplitude. So this is your peak value or this is your amplitude. And then since this is a sinusoidal waveform, so we have your sine omega t. dt. So we get the integral, okay? So in finding the area under the curve, we usually get the integral of that waveform. So since this is a constant, so period 2 pi, okay? So full cycle. So full cycle in radians is equivalent to 2 pi. Okay, so that is we put this out since this is a constant. So we have your Vm all over 2 pi, and then we integrate your sine omega t. So the integral of sine omega t is negative cosine omega t. That is from 0 to pi. Okay, why 0 to pi? Because we are only considering one cycle, because our next cycle is equivalent to 0 because it is reverse biased. We cannot see any output during this one. Okay, so evaluating negative cosine omega t from 0 to pi, that will give you negative cosine 0 is 1, and then minus, okay, it will become negative 1. So, minus negative 1, it will become 1 plus 1. So, this is 2. Okay, so this is equivalent to 2. Canceling this out, that will give us the peak value or the maximum value divided by pi. That is where your 0.318 came from. Okay? So you can always remember the derivation, or you just remember that the average or DC voltage that we have when we have a half-wave rectifier is 0.318 of your peak voltage. Okay? So since we're talking about peak voltage and the RMS voltage is given, always remember that your VRMS, okay, the voltage RMS is equivalent to peak voltage divided by the square root of 2. Okay? So therefore, if you need to solve for the peak voltage given the RMS voltage, it is equivalent to VRMS multiplied by the square root of 2. So that is our relationship between the two. And when we say peak to peak voltage, okay, so this is your V peak, and when you get this total voltage here, this is what you say, the peak to peak voltage. Usually, the peak voltage and the peak to peak voltage, we see this when we are using the oscilloscope. But in worded problems, unless otherwise specified, usually it is in the form of the RMS voltage. So the 220 volts in our AC outlet, so that is RMS. Okay. So when we during what we call this surge, when we have a current surge, or for example, there was a power interruption, and then right away the power was turned on, usually we have a surge voltage. So that maximum voltage is what we call the peak voltage. So imagine you have 220, and then you multiply that by square root of 2. So how much is that? So you have 220 multiplied by the square root of 2. So that will give you up to 311 volts. So when your appliances was is being connected to that, there's a tendency that your appliances will be destroyed because it is just rated at 220. So sometimes we place voltage regulators. So therefore, if we experience those surge voltage and currents like that, your appliance will still be protected. Okay? And sometimes we have a fuse, but I think we have a new here, like there's a new design for those type of occurrences. Okay? um like that. So peak voltage is different from the RMS voltage, and the 220 volts is an RMS value. Okay, so it's not a peak voltage. Okay, so to continue, what if we have here a specific diode. So it's not an ideal diode, just like what we did a while ago. So if it is not an ideal diode, we have here, let's take for example, this is a silicon diode. So you have here a zero point 0.7 volt drop. So when your diode is in the forward bias stage, so it has a zero point 0.7 voltage drop. So your peak input here will no longer be your output here. However, that will become your input peak minus zero point 0.7 because you have a zero point 0.7 volts drop here. So your output voltage now becomes V input minus zero point 0.7 volts. Okay, so that will be the effect of if you have a barrier potential on your half-wave rectifier circuit. Now, we have talked about this on our last video. So, the peak inverse voltage or PIV. So, this is very important because automatically your diode can experience a negative voltage every time that the signal goes reverse. So therefore, that is what we mean by peak inverse voltage. Okay? So during positive half cycle, when your diode is conducting, no problem. But when your cycle goes negative, your diode will experience a negative voltage. And we have to be very careful that it will not exceed the PIV rating of your diode, because if it does, it might destroy your diode. Okay, so your peak inverse voltage or PIV is equals the peak value of the input voltage, and the diode must be capable of withstanding this amount of repetitive reverse voltages. So for example, my PIV here is 10 volts. So I will not apply a peak voltage here that is greater than 10 volts, because during negative half cycle, let us say 12, my diode can experience a negative 12. If it can handle only up to negative 10, so therefore it will be a reason that your diode will be destroyed. So to be careful, okay, to be sure that our diode will not be destroyed during the process, what we do is we're going to make use of diodes with PIV. We're going to make use of an input voltage which is equal to the PIV of your diode. So if our PIV here is equal to 25 volts, therefore, what we can do is use also a 25 volts input here, not exceeding 25 volts. Okay, so that our diode will not be destroyed. So usually, we do not connect your input signal directly to your rectifier circuit. So, in practice, okay, for safety purposes also, for isolation purposes also, we make use of a transformer. Okay, so we make use of a transformer to couple your circuit to the AC source. Okay, so we have here a half-wave rectifier with transformer coupled input voltage. So what is a transformer? So transformer is used to couple the AC input voltage from the source to the rectifier. Okay, so it allows the source voltage to be either stepped up or stepped down. So we have two types of transformer. We have a step up transformer and we have a step down transformer. So if we wanted to make your voltage higher than its primary voltage or its source, then we make use of a step-up transformer. But if we wanted the voltage to be lower than your primary voltage or your input voltage, we make use of a step-down transformer. Okay? So, the AC source the AC source is electrically isolated from the rectifier. So if anything happens to the AC source, since they are not connected directly, so it will not destroy your rectifier circuit. So that is also one reason why we make use of a transformer to couple your input signal to your rectifier circuit. Okay, so in using a transformer coupled input voltage, we will analyze, or we will be needing to understand these different parameters. So we have here your N. What is your N? N corresponds to the secondary winding of your transformer and to the primary winding of your transformer. So there can be three values for N. Okay? So what are those three values for N? So since this is equal to since this is N is equal to the secondary winding all over the primary winding. Okay? So when n is greater than 1, okay? So when n is greater than 1, that means your secondary or your numerator is greater than your primary. So therefore, that means that you have a step up. You have a step-up transformer because it is greater than 1 since your numerator is greater than your denominator. That means your primary voltage is lesser than your secondary voltage, or your secondary voltage is greater than your primary voltage. So you are stepping up the actual input voltage. Okay? Now, when our N is lesser than 1, that means we are using a step down. We are using a step-down transformer. That means, okay, our primary voltage is greater than our secondary voltage since it is less than 1 because this is greater than your numerator. Okay, and then when we have n is equal to 1, the primary, okay, the primary voltage is just equal to the secondary voltage. So you might be asking, why will I use a transformer if my primary is just equal to the secondary? So for the second reason of safety, because there is an electrical isolation between the input and your output signal. Okay, so we will be using this secondary and primary winding in determining, okay, your solutions for half-wave rectifier circuits. So N, we have to determine first whether your transformer is a step up or a step down transformer. And then we have to solve for the secondary voltage. The secondary voltage is the one which will be applied to your half-wave rectifier circuit. Okay? So your secondary voltage is equivalent to N multiplied by your primary voltage. Okay? So we have here your output voltage. So, secondary voltage is different from your output voltage. The secondary voltage is the voltage that will be applied to your half-wave rectifier. Your VP output is the output of your rectifier circuit. So, V secondary is your input. It will serve as your V input, while your V output is the output of your half-wave rectifier circuit. And that is equivalent to the secondary voltage minus 0.7, considering that we have a silicon diode here. Okay? And then your PIV is just equivalent to the secondary voltage or your VP secondary. Okay? So this is how your half-wave rectifier. So this is your half-wave rectifier consisting of a single diode and your load resistance. This is where we are actually getting your output. And then this is your transformer. Okay? So this is your source. As you can see, your source is not directly connected here. What is connected here is your transformer. So if anything happens to the source, okay, this will not be destroyed because it has no physical connection. Okay, so there is no physical connection between your primary source, and likewise our input here will not be the one to be rectified. Why? Because we have still here a transformer. So whatever your secondary voltage here will be the one which will be rectified by your half-wave rectifier circuit. Okay? So if we have here an example, we have here first, determine the peak value of the output voltage. Having this one, determine the rectified peak output voltage, determine the average voltage, and what is the PIV of the diode. So in this case, we are given here the peak value. So the peak value is 156 volts. So therefore, we have here a positive 156 and a negative 156. So during the positive half, no, not yet. So this is the primary voltage. We still need to compute for the secondary voltage, that is determine the value of the output voltage here. What will be the value that will be our input for our rectifier diode? So we are given here a 2:1. Okay, 2:1 transformer. So what do we mean by 2:1? 2 is the primary winding and 1 is the secondary winding. Applying the formula now, okay, applying the formula, we have here your secondary winding, your secondary voltage is equivalent to N multiplied by your primary voltage. So that is equivalent to N multiplied by your primary voltage. What is N? N is equal to the secondary winding divided by the primary winding. The secondary winding is 1 and the primary winding is 2. So your N is equal to 1 half or zero point 0.5. 0.5 is less than 2. So what do we mean by that? That means we have a step-down transformer. So we are stepping down your 156 volts by its half. Okay? So therefore, the one that will reach your rectifier circuit is equivalent to N multiplied by the primary voltage. So that is 1 half multiplied by 156 volts. That will give us 78 volts peak. So this is the peak value. Okay. So this is the one which will be which will be applied to your rectifier diode. So during positive half cycle, that will have positive 78 volts, and during the negative half cycle, that will give you negative 78 volts. Okay, now the question is determine the rectified peak output voltage. So upon passing here, so this is not an ideal diode. Okay, so this is not an ideal diode because we have here 1N4002. So this is an example of a silicon diode, this family of diode here. 4001, 4002. This is the usual diode that we use in the laboratory. Okay, so what is the output now? The output now is during positive half, you have 78 volts, then you have to subtract 0.7 volts here. So you have here 78 volts, okay, minus 0.7 volts. So your output rectified voltage now is equivalent to 77.3 voltage peak. Okay, then we have to solve for the average voltage. So what is the average voltage? Average voltage is your VDC. So your VDC is 0.318 of the peak output voltage, which is 77.3 volts peak. So that will give you 24.58 volts. So if you have a voltmeter and you're going to measure the DC source, the DC voltage across that load resistance, you can measure 24.58 volts. So out of 77.3 volts, 24.58 there was converted into DC. And lastly, what is the PIV of the diode? So the PIV of the diode is equivalent to 78 volts. Why not 156? Because 156 will not be experienced, negative 156 will not be experienced by the diode. Okay, so what will go through the diode during the reverse bias condition or during the negative half cycle is the negative 78 and not the 156. That's why our PIV rating for that specific diode must be equal to 78 volts. So those are the some of the things that you can compute or can encounter when you have a half-wave rectifier. Okay? Now, let us go to full-wave rectifier. So, what is full-wave rectifier? A full-wave rectifier allows a unidirectional one-way current through the load during the entire 360 degrees of the input cycle. Take note that at the using half-wave rectifier, we only conduct for 180 degrees. Why? Because during the next one-half cycle, your diode is automatically in the reverse bias mode. So therefore, it is not conducting. So there is only a current during the first 180 degrees. Okay, so for full wave, we are assured that we can conduct for the entire 360 degrees of the input cycle. So we can conduct for the entire 360 degrees of the input cycle. Okay, so we have here an output voltage with a frequency twice. Okay, so um in here, okay, always remember that the frequency of the input is also equal to the frequency of the output. So the frequency of your input signal is equal to the frequency of your output signal. So if the frequency is 60 hertz at the input, so at the output your frequency is also 60 hertz. So they are just equal. Okay? So however, for a full wave rectifier, we have here an output voltage with a frequency twice the input. Why? Because during the first cycle, what is the first cycle here? During this one, you have repeated 2 cycles already. So that means you doubled the frequency. Okay? So if this is one period, that will give you 2 cycles already. So you already have the doubled your frequency. So if your input frequency here is F1, so during full wave, it will become 2 times your F1. So always remember that. Okay? And from our derivation earlier, all you have to do is to apply 2 here, because you are already having an output during both half cycles. Unlike earlier, this is 0. So this is 0. So this time, we have another input signal. So all you have to do is to add 2 here. So if you add 2 here, then, so from 0.318, it became 0.636 of your peak voltage. So we have increased the amount of DC voltage that we have produced from your AC source. Okay? So if this is our input signal, okay, positive and negative half, upon passing through a full wave rectifier circuit, it becomes like this. So it is not totally DC, not yet a straight line, but we call this pulsating DC. Okay? With proper filtering, we can make this a almost DC. Okay? Almost, because only 63.6% was converted into DC, or the average voltage. Okay? So there are 2 types. Okay? There are 2 types of full wave rectifier. First is the center topped full wave rectifier. So this is what a center top full wave rectifier looks like. Okay, so it uses 2 diodes. Okay, so connected to the secondary of a center top transformer. So the input voltage is coupled through the transformer to the center top secondary. Half of this total secondary voltage appears between the center top and each end of the secondary winding. Okay, so this is how your center top operates. So we have here your input, and then we have here your transformer. So your transformer is center top. So let us place your load here. So we have here your first diode, and we have here your second diode. So when we say center top transformer class, so if this is our full secondary voltage, okay, so this will just have half of those 2 secondary voltages. So this means this is secondary divided by 2, secondary voltage divided by 2. Okay, so this first circuit here will have half of that secondary voltage, and then this circuit here will have half of that secondary voltage. Okay, so let us say during positive half cycle. So what do we mean by during positive half cycle? So during positive half cycle, this will give me plus or minus my input, and this will also give me plus and minus my input. So positive, which is connected to the anode, this first diode here is forward biased. Negative is connected to the anode. So that means this second diode here is reverse bias. So no current will flow here. However, there is a current which will flow across your first diode. So if we're going to have a loop here, we have here plus and minus. So this is your output voltage. So what is your output voltage? So we have here your input voltage. Okay, positive V in, and then we have your diode here, considering first that this is an ideal diode, and then we have here minus VO. So we have here minus VO is equal to 0. So what is your VO now? Your VO is equal to your V in. Okay, so what happens is, if this is our input, what is your output? That is also your output here. Okay? Now, what happens during the negative half cycle? So, during the negative half cycle, okay, so during the negative half cycle, this will become minus plus your input, and this will become minus plus your input. Okay, so this positive here is connected to your anode here. So this diode is now forward biased, while this diode here is reverse biased. So this is open. So where will the current go? The current will flow from negative to positive, and then it will be in this manner. Look, they have the same direction with the diode symbol, and then we go here, since this is already open, so it will enter here plus, and then it will leave here minus. So we have here minus plus VO. If we're going to follow the loop, we have again here V in plus V in, you have minus VO is equal to 0, wherein your VO is equal to your V in. Now, what is this V in, class? This is positive. We didn't see any negative sign here. And as you can see, okay, both of this, during positive half, this is the direction of your output, minus plus. And during the negative half, it is also minus plus. So during positive and negative half cycle, our output, so during the negative half cycle, our output is also positive. So this is our full wave rectifier. Positive half, we have a positive output. Negative half, we also have a positive output. So this is the output for your full wave rectifier. Okay, so that explains that. Okay, if we place a diode here which is silicon, all you have to do is to subtract 0.7 in your V in. So it is just the same. Okay, so your PIV, so since this is only half, in reality, if this became open, the entire voltage here will be experienced by your diode. The entire secondary voltage here will be experienced by your diode. Therefore, it is 2 times VP out, or simply your secondary voltage. Since this is your VP out, that is just 1/2, we will be considering a PIV of both of the whole secondary voltage here. Will not divide it into 2. So we have here 2 VP out plus 0.7. So why 0.7? Because during the time that this is open, one diode is conducting. So therefore, it is included in the reverse bias open circuit here. Okay? So we have here an example. It says here, show the voltage waveforms across each of the secondary winding and across RL. Okay, so across the secondary winding class, the secondary winding here, so this is your ano, okay? So if we have here your half wave, so your secondary is 100 multiplied by 1/2. So where this 1/2 came from? So again, we have 2:1. Okay, so this is 2:1. So therefore, our N there is 1/2. So we are stepping down your input voltage. So from 100 peak, so this is 200 volts peak to peak, but we are going to consider only the peak voltage. So 100 peak. So this is the secondary the secondary voltage is equivalent to 50 volts. Okay, just 50 volts. However, class, okay, that 50 volts will not, okay, so that 50 volts will not go directly to each diode. Okay, so it will not go directly to each diode. Okay, so this is 100 multiplied by 1 half. So the secondary voltage is equivalent to 50 volts. However, using center tap transformer, so using center tap transformer class, this will only give us plus and minus 25 volts, and this will only give us plus and minus 25 volts since we are using center tap. So the total secondary is 50, but each diode will be receiving only 25 volts. Okay? So how does your voltage waveform across each secondary winding? So this is a sinusoidal waveform with a 25 volts peak. This is also a sinusoidal waveform with 25 volts peak. Okay? So how about across RL? So across RL, it is already a This is across RL. So this is already your output waveform across RL. But what is the peak voltage here? So the peak voltage here is equivalent to 25 volts minus zero point 0.7. So this is equivalent to 24.3 volts. Okay? So because we only have zero point 0.7 volts there. Okay? So that is what we say, this is a full wave. So every time you look for a full wave, this is how it looks like. It's just a matter of what will be the voltages at the peak voltage. Okay? So what is the PIV? To PIV is twice your output voltage plus zero point 0.7. So what is your output voltage? Your output voltage is 24.3. So that is 24.3 multiplied by 2. Then we have plus zero point 0.7. So this will give us 24.3 times 2 plus zero point 0.7. So this will be 49.3 volts. So the PIV of your diode must be equal to 49.3 volts. Okay, so that is how you analyze a rectifier circuit. Okay, so this type of rectifier circuit uses two diodes and a center tap transformer. So for a center tap transformer, we are assuming that the upper circuit, the upper diode here and the lower diode here gets an exact input voltage, ideally. Okay, so if the secondary voltage is 50, like in our case, each of them will get 25 volts during the positive and the negative half cycle. Okay? Now, we have a second type of diode, full wave rectifier diode. So, this is what we call as the bridge full wave rectifier. So, for the bridge full wave rectifier, we do not use, okay? So, we do not use a center tap transformer here, but rather we use four diodes, okay? So, how does this operates? Okay, how does this full wave operates? Okay. So we have here four diodes, okay, in this manner. So let us say this is your load. Okay, this is your load resistance, just the same. So this is grounded. And then this is coming from the transformer. Okay. Oh, sorry, this is not connected. Okay, so this is connected here and this is connected here. Okay, so this is your secondary voltage. So this is your secondary voltage. Okay, so let us call this diode 1. This is diode 2. This is diode 3 and this is diode 4. Okay, take notes of the names of the diodes because sometimes some other books make use of this as diode 1, diode 2, diode 3, diode 4. You might be confused, okay? So you just have to look at their positions. So during the positive half cycle, what happens? Okay, so this means we have here positive and this is negative. Okay, so positive and this is negative. So that means your positive is here and your negative is here. As you can see, during the positive half cycle, this D1 here is forward biased. So why forward biased? Because positive is connected across your anode. Positive is connected across your cathode. That means your D3 here is open. So this is not functioning. That is an open circuit. Okay, if we're going to look at this position here, minus or the negative terminal is connected across this anode. So therefore, this is for reverse bias. So this is open. Current will not flow there. However, this is minus and this is cathode. So this means this is forward bias. If we're going to trace for your current, so this is your input at the secondary, your current is flowing from the negative to the positive. So negative to the positive, it will flow here. Oops. At this junction, your diode will be dividing, supposedly. However, this is open. So there is no other way for your diode to go but to pass through your D1 in this direction. So as you can see, this is the same with the direction of your diode symbol. Okay, and then afterwards, at this point, it will divide into two, supposedly. However, D4 is open, or this is reversed. So there is no other way for the current to pass through except through your load resistor. Your load resistor here is positive, this is negative. So your current will flow at this manner. So let us call that V out. Okay? And at this point, since this is open, it will pass through again your diode here, same direction with your D2 here, and then towards here. So you have a complete cycle. Okay? So if you're going to look at that, you have positive VI, we have here minus, okay? It left here at minus VO. Minus VO is equal to 0. So what is your VO? Your VO is equal to your VI. So this is during the positive half cycle. Okay, now, what happens during the negative half cycle? So this is minus plus V in. Okay? So this is minus plus V in. That means we have a negative terminal here. We have a positive terminal here. Okay? So this is your D1, this is your D3, this is your D2, and this is your D4. So in this condition class, okay, in this condition, your D1 and your D2 are both forward biased, while your D3 and your D4 are both reversed biased. Okay, so let us analyze what will happen in this condition. So in this condition, D1 connected, anode connected to the cathode, so D1 is open. So this is open. Negative, negative, so this is forward. So this is where your current can flow. How about here? So D4, positive connected to the anode, so this is forward. Positive connected to the cathode, so this time this is open. This is open. Okay? So how does your current flows here? So your current again flows from negative to the positive. So we have a loop here going here. Oops. Since this is open, Where are we going? So we're going through D4. Okay, so same direction. Okay, at this junction, this is open. So where will be our current going? Where will be our current flowing? So we have here your direction here. So this is plus, this is minus, and this is your VO. And then again, this is open. So your current will be flowing across D3. So look at them. Same direction. And then going back here. The cycle continues. As you can see, if we're going to trace it, we have here positive V in minus VO is equal to 0. Our VO is again positive V in. Just the same. Just the same of what we have here. And look at the direction. Plus minus VO, we have here plus minus VO. They are just the same. Okay? So, the only difference is this time, D1 and D2 are the one which are reverse biased, while now D3 and D4 are the one which are forward biased. But we have a complete current flow. So, during the positive half cycle, what is your output? V out. During the negative half cycle, what is your output? Also like this. So we just have the same output. Okay? And the DC produced here is equivalent to 0.636 of your peak voltage. Okay? So what is the implication if we're going to make use of A? So this is the explanation class. During the positive, so D1 and D2, they are the one which are forward bias, so the current will flow across them. And during negative half cycle, D3 and D4 are the one which are forward bias, so the current will be passing through across them. So we have here your output waveform. Okay, so take note that during positive and during negative, we have two diodes that are conducting. Since we have two diodes that are conducting, your VP out is equivalent to the secondary voltage. This is for ideal. For non-ideal, we have your VP output here, which is equal to the secondary voltage minus 1.4. So why 1.4? Because during positive or negative half cycle, there are always two diodes conducting, either diodes 1 or 2 or diodes 3 and 4. Each of those diodes have zero point 0.7 volts. So therefore, both of them, that will give us 1.4. Now, for the peak inverse voltage, so your PIV is equal to VP out. For PIV here, that is equal to VP out plus 0.7. Okay? So that is your voltages, or that is your voltages. And then, of course, VDC is equal to this one, 0.636 of your VP. So this is the same with the transformer coupled and with the bridge rectifier. Okay, they have the same output, they have the same output waveform, they have the same output DC voltage. The only difference is their circuit. So the other one makes use of two diodes and a center tap transformer, while this one, they don't have a center tap transformer, but they make use of four diodes. Okay? But in reality, it is the bridge rectifier that is most commonly used. Okay? Because center tap transformers are very bulky. Okay, so comparing two diodes to four diodes are just a small component compared to a center tap transformer. Therefore, when you look at power supply circuits, mostly they make use of the full bridge compared to a center tap transformer. Okay, but anyway, any of the two, that will give you an output which is equivalent to the output of a full wave waveform. Okay, so there is a set work here. Okay, so I will be placing a drop box in our school book for you to answer this set work. So this set work is very easy. So this is just a follow up if you understood what we have discussed in this video. Okay, so the second video will be about clipper and clumper, so you just have to wait for that. Okay, so for now, I will have to leave you with the sit work. Okay, thank you very much for watching and have a nice day. Bye.